Welcome to the first live session of the Robust Vision Challenge 2020. You can see our introduction video, closing videos, and the keynotes on the ECCV virtual conference platform. But I will shortly recap our motivation and background of the workshop. If you use computer vision systems and solutions that perform very well on public leaderboards, you very often see that in real life they don't perform well. The performance breaks and it's not really usable for your task. What's the reason behind this? Well, the main contributors are the dataset bias and the gamification, where gamification is about that we want that participants of leaderboards are solving the leaderboard or the challenge of the leaderboard and not the actual task behind it. So the RVC idea was now that we are creating a meta challenge where we combine the multiple benchmarks into one meta challenge. So you have to submit the same solution with the same hyperparameters to multiple benchmarks, and then we combine all these rankings into one final ranking. So you have to perform well on all of the benchmarks, not just on one. This is a joint effort of 28 organizers. You can see them all lined up here. We had very much effort to make this workshop possible and the challenge itself. So thanks to every one of you. You did a tremendous job, and it was a lot, and especially in these times, thanks for doing all this work. Also, I have to thank all our sponsors. It's not a given that we get financial support during the crisis we have here, the global one. So thanks a lot to our golden sponsors, Apple, AIT, Google, Intel, and to our silver sponsors, Naval Labs Europe and Mapillary Research. We also have 3 keynotes from 3 very distinguished presenters. The first keynote is from Ross Gershik with the topic Robustness Across the Data Abundance Spectrum. The second is from Kwok Lee, Noisy Student Training for Robust Vision. And the third is from Alexander Matry, What Do Our Models Learn? You can watch all of these videos on the ECCV virtual conference platform, and they are put online after the conference on our website, robustvision.net. We now continue with the winner ceremony. Of course, it has not the same glamour as a physical live winner ceremony, but we will make do with this presentation. So we start with the stereo competition. The first place in stereo competition goes to the CFNet, Cascade and Fused Cost Volume for Efficient and Robust Stereo Matching by Selun Shen and Yu Chao Dai from the Northwestern Polytechnical University and Peking University. The second place goes to NLCA-Net version 2 for stereo matching from Ziba Rao, Mingyi He, Boli, Renjie He from the Northwestern Polytechnical University. Congratulations. We now continue with our optical flow competition winners. The first place goes to a TensorFlow implementation of Raft by Dekin Son et al. From Google Research. The second place goes to Pyramid Recurrent All Pairs Field Transformations for Optical Flow Estimation by Sexion Wan, Yuxin Mao, Yu Shao Dai from Northwestern Polytechnical University. Congratulations. Now to the MonoDev prediction winners. The first place goes to our own baseline, BTS trained by our team by Hendrik Schilling and the Rabbit AI crew. As this is a baseline from the organizers, it does not receive part of the prize money. The second place goes to revisiting robust metric depth prediction from single images from Ke Xian, Hongwei Zhao, Xin Xiong, and Xiura Cao from the Haozhong University of Science and Technology. Now to the object detection winners. The first place goes to learning a unified label space for robust object detection. Xingyi Zhao, Vladen Kulturn, Philipp Krähenbühl from the Intel Labs and UT Austin. And the second place goes to WiseDat from Yunxin Huang, Yia Qi Fan, Xiao Chaoun, Yu, and Xiao He from Visa AI Labs, Hong Kong. Congratulations. Semantic segmentation, the first place goes to multi-domain semantic segmentation with pyramidal fusion by Marin Orsic, Petra Bevendic, Ivan Grubisic, Josip Saric, and Sinisa Sevic from the University of Zagreb. And the second place goes to our own baseline, MSEC 1080 from John Lambert, Zhuang Liu, Ozan Zeneas, James Hayes, Vladan Kulton from Intel Labs, UC Berkeley, Georgia Institute of Technology, and Argo AI. As this is a baseline, it does not receive financial prize money. For instance segmentation, we only have one submission, one valid submission. This is the first place, learning a unified label space for robust object detection, which was also one of the submissions for the object detection task. From Yingzi Zhuo, Vladan Kulton, and Philip Granbuhl from Intel Labs and UT Austin. And finally, Panoptic segmentation. We have one submission, one valid submission from EFFPS from Rohit Mohan and Abhinav Valanda from the University of Freiburg. Congratulations. So to maximize the time that presenters have from our challenges, we will not recap the keynotes or talk about the keynotes, but we go ahead and start with all the presentations. So we start with CFNet, the first place from Stereo.
Hello everyone, my name is Zhe Lun Shen. I'm very glad to introduce our work in this live session. This work is finished by me and my tutor Yuchao Dai. Now let me begin my presentation by introducing the motivation of our work and the challenge we met when participating in the Robust Challenge 2020. Our goal is to construct an efficient and robust stereo matching system. Towards this goal, one major challenge we need to solve is to balance different disparity distributions across different datasets. As we show in this slide, the disparity range of different datasets is totally different, especially the disparity range of mid-berry is extremely large. One straightforward solution seems to densely sample the whole disparity range. However, such approach is usually time-consuming and GPU memory unfriendly, which goes against our motivation. So, is there anything we can do to achieve a more efficient system? The answer is yes. Cascade Stereo is a work published in this year's CVPR. It only needs to densely sample the course's scale cost value and then narrow down the search range of next stage. Inspired by it, we propose a cascade and full cost value to construct a more efficient system. The overall architecture of our model is shown in this slide, which consists of three parts: pyramid feature extraction, cost value fusion, and cost value cascade. Given an image pair, we first import a unit-like encoder-decoder architecture with skip connections to extract multi-scale image features. Then, in the cost-value fusion part, we use both feature concatenation and group-wise correlation to generate low-scale cost values, respectively, and fuse them by encoder-decoder process to get the initial disparity map. The architecture of our cost-value fusion model is a little similar to the hourglass network proposed in PSMNet. Specifically, we first import 4 3D convolution layers with skip connections to regularize each cost value, and then we integrate corresponding scale value into the downsampled cost value by concatenation operation as a future dimension. And then we use one more hourglass network to further regularize it. Given the initial disparity map, the next step is to iteratively narrow down the disparity range and refine disparity maps in a cost-to-find manner. Considering the next stage disparity searching range, Uniform sampling a predefined range is the most straightforward way. However, such approach assumes that all pixels are the same and cannot make adapt pixel level adjustments. For example, we should expand the searching range of ear-posts and occluded pixels. To check this problem, we propose an adaptively variance-based disparity range uncertainty estimation. Our idea is inspired by the property of final cost value. Typically, final cost value reflects the similarities between candidate matching pixel pairs, and the true matching pairs should have the highest similarities. Thus, the ideal cost value should be unimodal distribution at each position. However, actual cost value is predominantly unimodal or even multimodal distributions at some pixels. So it is necessary to define an uncertainty to measure the confidence of disparity estimation at each position. The formula of our uncertainty is shown in this slide, and it can also be regarded as the variance of disparity D. Obviously, the uncertainty of unimodal distribution equals to 0, and multimodal distributions tend to have high uncertainty. Therefore, we can employ uncertainty to evaluate the confidence of disparity estimation and use it to generate the next stage disparity searching range. For example, a higher uncertainty implies a larger search range, but it iteratively narrow down the disparity range and higher the cost value resolution. We can refine the disparity in a cost-to-find manner. Here is the result. As shown in this table, our method shows great generalization ability and perform well on all three datasets. What's more, if you pay attention to the detailed sub-rankings, you can find that our method also ranks first on some metrics of Katie and Midbury, like the D1FG of Katie and BET 0.5 to BET 2.0 of Midbury, which proves that the gap between our method and the #1 approach on sub-dataset is extremely tiny. Finally, let me make a short conclusion. The key point of our method lies in the fuse and cascade cost value representation. Firstly, we employ a cost value fusion model to fuse low-scale cost value and get the initial disparity map. Then we use a variance-based uncertainty estimation to get the next stage disparity searching range. By iteratively narrow down the disparity range and higher the cost value resolution, the disparity is refined in a cost-to-find manner. By the way, our code will be released after the publication of our paper. So if you are interested in our work, please keep watching us. That's all. Thank you.
Okay, thank you for your presentation. Well, the Q&A in this whole setup currently works that you can enter questions in this Q&A panel, and I can then post them basically. If questions, of course, come from the panelists, then just go ahead and ask them. I might kick off the Q&A session. Selun, you showed in one slide that one of the main problems for you was the many different disparity ranges. Did you see any other dataset related problems or dataset bias basically that you had to deal with? Would removing one of the leaderboards or one of the challenges made life easier? What if you had to remove one of the three challenges from the meta challenge, what would it be and why? Just from a tricking the system perspective.
Yeah, I think other challenge we met maybe the ETH3D is gray images and Midbury and in contrast, the Midberry and the KT are RGB images, so it may make some difficult to make a balance between gray images and RGB images. And what's more, the resolution of Midberry is very high, which maybe is 2 times larger than ETH3D. So we select to downsample 2 times, downsample the images of Midberry to a close size of KT and ETH3D. That's all.
Okay, thank you. We have one question from the audience. Anonymous attendee asks, how do you train across the 3 data sets? Maybe this refers to the technical aspect of it, how you combine the data sets?
Thank you for your question. Actually, the training strategy is also an important part of our work, which we don't discuss in the presentation because of time limit. Actually, we propose a 3-stage training strategy to train our network. Firstly, we pre-train our network on TensorFlow dataset. Secondly, we fine-tune our model with a combination of 3 datasets, KT, ETH3D, and Midberry for 400 epochs. Finally, we augment Midberry and ETH3D to the same size as KT and fine-tune our model for 50 epochs with a small learning rate. If you want to know more details, you can also see our technical report where we describe our 3-stage training strategy in detail. That's all. Thank you.
Thanks. So did I get this right? Your native resolution is basically the Kitty resolution, right? Of the network you are using.
Yes, you are right.
And large, so large scale evaluation images, you crop them and then do multiple passes, or do you scale them?
Actually, we just random crop all pictures to a fixed resolution. What we did what we did is just cut the images to 256 multiplies 500.
Sorry, I didn't get the last part.
Yeah, we just random crop all these images to a fixed resolution. Like for example, 256 multiplies 512. That's what we did during training process.
Okay, I see. We got another question here about your GPU setup. How many GPUs did you use to train, and then for the fine tuning, and what specs did the GPUs have? What was your computing power basically?
Actually, we set the bench size of 8 and train it on 4 1,000 and 1,000 and NVIDIA 1080 Ti GPUs, or you may also select V100 to train our model.
Sorry, so you use the V100 to train, or is this a possibility? What did you actually use?
if you use the V100 to train our model, you just need to use 2 V100 with a bench size of 8. And if you use NVIDIA 180 Ti to train our model, you need 4 GPUs to train our network with bench size of 8.
Yes.
Yeah.
Rodrigo, you have an input, please. Oh, no? Okay. Is there another question? The memory and GPU requirements in the I think it's the same question, right? Maybe what are the requirements to execute the model for inference? So if not for training, just for inference.
I think it may be 3000 MB you need to use to when testing KT and the ETH3D, because Medberry, the resolution of Medberry is sorry, I think maybe 6,000 MB you need to use to test KT and ETH3D with a full resolution. And because Medberry has the highest resolution in all these 3 datasets, so you need to use you need 2 times larger GPU memory to test Medberry, to test the images of Medberry. That's all. Thank you.
Thank you. Is there any other open questions? Please type them in the Q&A section. If one of our panelists wants to post a question, go ahead. Okay, I think we continue with our next presentation. This is the NLCA-Net. This is the second place for stereo. Please start sharing your screen. And Selung, please stop sharing your screen. You have to select stop sharing at the top of your screen.
Hello, everyone. Thank you, organizer.
Hi.
Okay.
Yes, it's working.
Can you see?
Yes, please continue.
My name is Min Yihe from Northwestern Polytechnic University for the sixth presentation. Okay. This is our university from the Xi'an and also from my group. Now is overview about this talk, background and motivation, and then talk about the new model and the strategy. Finally, give the results and the discussions. So the first author is my student, Zibo Lao, and also with other young teachers together. This is the background and motivation. Actually, for the RVC problem, actually for stereo matching, flow, and many different topics. In recent years, has many progress because the CV has with active for this problem is wide applications, especially for deep learning. So this CV problems has great progress, but still has some problem because this is mostly limited to single task, single dataset. We call this is STSD. The challenge is because the dataset normally is imbalanced and also load for multi datasets. Of course, the first year is before last year have the organization. Also, for the problem is multitask and multi-datasets. For this challenger, these are single task and multi-datasets. We call this. This is for stereo matching. So this is the trend for our testing. The challenger is the RVC, especially for the stereo matching. For example, the dataset 1, dataset 2, dataset 3, all 3D separately progressed with different methods and different results. For this track, our motivation is to improve the model's performance on the small datasets and also to reduce the effects on the multi-datasets. Here, three datasets. This also shows us about the stereo matching progressed in the recent years. But now, how about the multi-datasets? Here, three datasets. So our motivation is design new network and also use the new strategy. The network is basically based on our recent work that's published in last month here, Pascal transaction, signal and information processing in July. So can find the detail. Actually, this has been demonstrated and the top one in the HVE geoscience remote sensing website. And also we will give the implement some changes to this network. Because this network, we have the 5 models, but here just talk about the cost value, refinement, normalization. Finally, we'll resync the pre-training and the data augmentation. CFNet, this is a new model. Actually, this is an extension of our recent work, NLCA-Net, that's published last month. This is mainly network. So the detail I will don't give the detail here because the time limited, but you can find this code and also this paper. For this, the extension, that's version 2 for this model. We only focus on this part. This part and this part is are changed, improved, and also some normalization and activation functions inside, but not marked here. So there is 1, 2, 3 cost value construction, refinement model, and normalization. I will give the detail about this new changes after this work last month. This is cost value construction because we here use the calculate volume and variance volume together and combine. We use a combined volume to measure this for matching clear for improvement the performance. Secondly, refinement part is here. This is the model. This part is as a guidance model and also confident map, cost disparity, and ideal new refinement model can improve the results of the network by small margin. The third is about the normalization and activation function. Is actually this is inspired from the some reference. For example, the normally traditionally use the bunch normalization, but here we use a group normalization, and also this is a large work reference. I'm here to use a match instead of the ruler function. The main difference is here. We found this function is better to improve the performance. Part 3 is about the strategy. Strategy 1 is about the data, because the key issue RVC is about the datasets from the different source of datasets. But here, 3, Kitty, ETH3D, and Midbury. But here is only unbalanced. For example, here, this dataset has much number of the data, but this one, for this one, and this one is smaller. And also for the training data and the testing data, still very small. Actually, some work has been done before, for example, 2014, 2015, and 2017, these data sets and evaluated on the publications. But here, everybody knows that is balanced labels. So here has a problem. So for our work, we use the pre-training. Pre-training is very important, and also use data augmentation, because normally for probability need for the network, we should to for data augmentation, and also for pre-training use based initial network. The pre-training we use the Sentinel. The data is more than 35 images, but here and give the results here. So for the extension, the version 2, we get the results here. It's much better than the before. This is use the data augmentation, especially for rhythm cropping and also shift movement. We only use this, and also, for example, here, because this dataset 2 and dataset 3 are very smaller, we just use some, for example, that's 27 by 10 times and 10 times, but still within the way smaller. This is some picture about the after this result. Here is just give the table for comparison. For Kikia 2015 dataset, this is our performance. This is just the first presentation Professor Dayusa and the students sent. They just give. But mainly, most of the performance for our method is for the first one. For dataset ETH3D, but normally the second best one. For dataset 3, mainly for the best second one, but for the number 1 and the number 2, they are normally for the best one, more best one index. So that's the results. Here we have an interesting. You can look at here. For data 1, data 2, and data 3, this one, the performance is 1.92, and this is 3.84. This is 10.4.
Is this bad pixel 1?
Much larger, but this is very smaller. So this because this test only one choice for submission. If we have second one and the third one, will be much better, because this one and this one can still have space to decrease.
Mindy, you are extending your time. Sorry.
Okay. Finally page. Also, the core data and can be found from here. We already released and this place and this place. This version 1, version 2.
Okay, thank you. Let's quickly start with the Q&A. In the last slide, you showed the bad pixel score, right? The percentage per data set.
Yeah.
Yes, okay, thanks. Are there questions in the audience?
Yeah, for these 3 different data sets, normally because we just make the data augmentation is with the same probability in the same way. So actually we can augment this data and this data with more data to train this part and this part to decrease this error. Yeah, decrease this error. Possibility toward better results for all the 3 data sets. But because this context only one choice, only one submission, so we cannot do a larger trial. So recently, I have done some experiments of this possibility will give them better results.
Okay, Mingyi, we have one question from the audience. For pre-training on scene flow, do you convert the RGB images to gray?
Yeah. Actually, we use for pre-training we use the data augmentation. Actually, for pre-training we use the SimFlow. SimFlow, that's publicly available. That data we have 35,000 images. This pre-training just for initial to get an initial network of our network. Thank you.
I didn't get your answer. Do you convert the images to grayscale, to single channel? Or can you use RGB?
Yes, RGB.
RGB, okay.
RGB, yeah.
Thank you. Is there another question?
So I have a question.
Daniel, please go ahead.
It's the same question that you asked earlier in the first presentation. How do you deal with the different resolutions? So when you evaluate and the images have different aspect ratios, how do you present them to the network, which presumably has a fixed aspect ratio as input?
Yes, about the resolutions, about the image resolution, or what means your resolution?
I'm talking about that.
Yeah, for the size is 515 to 256. Normally use this and make it smaller, maybe.
So if
normally we just use 512, 256.
If the input image doesn't have the same aspect ratio, then what do you do?
That's the size of the images we use. And also finally you use the, actually we use the 3-dimensional convolutional neural network. You use the many layers, that different layer with a different size of the resolution. The fixed one is the 512, 256.
Yeah, I'm not sure I understand how you deal with the different aspect ratio, but
I think Daniel wants to know if your image is larger than your native resolution of the network, how do you deal with that? Do you crop? Do you resize? What is the data policy for that?
Yeah, cropped it, randomly cropped it to 512 to 256. Yeah, actually, this can be found from our paper, recent paper that's available last month. I already showed here, and also the source code already listed, and the actually just show at this slide.
Okay, thank you. I don't see other open questions. So maybe as a question to the panel, as Daniel and Andreas are here, and is Thorsten also here? I don't know. We saw in the slides from Mingyi that there are these 3 data sets, and they have different disparity ranges and different sizes. But actually, the whole test set is very small. So from a robust evaluation perspective, we have very little data points if we evaluate algorithms. What is with the long tail distribution? What is with these one-off cases that can happen once every 100,000 hours of operation? We are just very far away from robustly evaluating stereo vision in my mind. What is your take on that, and how do you think we can change that?
Oh, actually, for different date and possibly, we still think about the evaluation parameters is very so important to how to handle the different size. And also, this possibly depend on the distribution. Normally, we just from our experience, but possibly for in the future, for example, this 3 datasets from this value, just give our insight to for next step how to build, for example, evaluation. For example, combined volume cost function to control this part and this part. But this test normally we just equally, but possibly we were for example this one the error is larger. Possibly I will give a control parameter. For example, lambda 1, lambda 2, lambda 3.
Okay, Mingyi, yes. Thank you.
Thank you.
And to Daniel and Andreas, maybe you want to comment. How do you think we can get a more robust evaluation of stereo vision going? What are your takes on that?
Or you want to go ahead? Okay.
Oh, so yeah, in the future,
no,
possibly.
Mingyi, this is a question to the panelists. Sorry.
Okay. Thank you.
I think
Andreas.
It was a question to the organizers, right? Yeah, it's a good question. I think we have seen, if you look at Ross Gershik's talk, I think this is the right direction to go, definitely. And we should have something like that for stereo. With the current data sets, I think it's difficult, right? Even Kitty is very small, so it would be good to have a much larger database and source somehow the challenging cases from there. And we have a lot of data, at least in the self-driving. I don't know, for Middlebury and ETH3D, I think maybe Daniel can comment, it's much harder because generating the ground truth is more laborious, and setting up the scenes and so on. Maybe that's harder. Yeah, so the problem is, of course, if we have, it's easy, I think it's relatively easy to get a data set with challenging examples. Also, there's the like the benchmark from Heidelberg, right, which evaluates these difficult weather conditions, etc. But you always need to have a diverse, you need to have a diverse set of data points, and you need to have the ground truth, and that makes it a bit more challenging. But I think, yeah, that's important to consider in the future. It's of course impossible with the existing data sets.
Daniel, what is your take on that?
Well, I mean, part of it is how to get more diverse training and test data, but the other part of it is to even encourage people to participate. I think the biggest danger is, I mean, there's no incentive really for authors to demonstrate robustness unless we have workshops like this. But if the reviewers don't demand participation on or measuring on many different data sets, I mean, you can see even with the small number of stereo baselines that we have right now, very few people still evaluate even on Middlebury because there isn't much training data, so it's much harder to get good results. But if you really did want to get bigger data sets, I mean, the two options I see, either do a better job creating more synthetic realistic data, and there are certainly efforts along those lines, especially since training data is needed. So there's replica or something, data sets like that become more and more realistic. So that's good. The other idea is to use pseudo ground truth. So you get large data sets that are just taken with iPhones, and then you use the iPhone depth maps, which are lower quality, but maybe that's a better technique for training rather than for testing.
Yeah, I fully agree with that. I think another aspect that's related is what do we actually want? I'm a big critique of these metrics that we're using at the moment. Like the pixel-wise evaluation, because on its own, it's rather without any utility, right? And so the question is really, what do you want to do with it? Do you want to do 3D reconstruction? But if you want to do 3D reconstruction, you don't look at a single disparity map. You look at a full 3D reconstructed scene that is using a lot of images and fusing things maybe. Or do you want to do self-driving? Or do you want robotic manipulation where the goal is really different, right? And then it's, I think if we talk about robustness, I mean, it's a big topic on its own, but if we talk about robustness, then we always need to keep in mind rather than just finding more robust metrics over different data sets, what is actually that we care about? And I think we should answer that as well.
Yeah, that's a whole question of its own. Yeah, thanks. We have to continue. Sorry to cut this short. Our next talk, we start now with the second place of flow. This has to do with timing constraints of the participants and the time zones. So the second place is BRA-flow. Are you ready to present? Mingyi, please stop your screen sharing. Thank you.
Thank you.
Okay, can you hear me?
Yes, go ahead.
Okay. Hello, this is Zhe Xiong from Northwestern Polytechnical University. I'm very glad to share our work on optical flow named PLA flow. This is a joint work with my supervisor Yu Chao and my friend Yu Xin. Let us first briefly review the definition of optical flow. It describes the pixel motion displacement between two adjustment images, which has been studied for decades. A typical learning-based model is CFNet, which combines primate feature processing, feature warping, and cost volume. A recent model named RAFT built all pairs multi-scale 4D correlation and iteratively update flows through a recurrent unit, which just won the best paper award at this conference. It got the certain accuracy and has good generalization performance with high efficiency. Our work is built upon it, a primate version of RAFT. The aim of Robust Vision Challenge is to push forward real-world usability and reduce dataset bias. However, most of the existing methods are specially optimized for specific datasets and cannot generalize well across datasets. We consider use multiple datasets for single model joint training. As RAFT is always work on a fixed low resolution and the primate structure has been widely used in early works, we propose to use the high resolution feature to preserve the details and combine them to achieve more robust and accurate high-resolution flow estimation. This is our model structure. We use RAFT updater as our flow update unit and primate processing low resolution to high resolution. Due to computational limitation, our network only uses 2 primate layers. We can see the difference between our model and RAFT from this table. Because we introduced a quarter resolution correlation, the number of parameters, running time, and memory consumption has been increased, but it works well. We will show the results later. Let me talk about the challenge in joint training. The first is about the Viper dataset. We noticed that there are many large unreasonable values in flow annotation, and the front cover is relatively large. This may have negative impact on model training, so we remove them at the training stage. We also made a statistic on motion distribution. The amount of small motion is the most in each dataset, but even so, Kitty has much more minimal motion than others. At the same time, the amount of data is also different. We need to set different proportion for different datasets to balance it. We use 4 GPUs and set best size to 4 for training. We first pre-train our model on flying chairs and flying scenes and fine-tune on joint dataset with this proportion. We use the same data augmentation strategy as RAFT. We submit our results to multiple benchmarks and won the 2nd place in this challenge. Here is the ranking on each benchmark. We go through this fast. Kitty is the first in this challenge. Kitty is the 2nd. Viper is the 2nd. Viper is the 3rd. Midbury is the 2nd. After the submitted results, I would like to share some of our discussions, our pre-trained model has good generalization ability. And as we expected, our model works well in small motion areas. This table is the metric from motion from 0 to 10 pixels and 10 to 60 pixels on Center. We won the first place in multiple small motion metrics on Center. It is also better in high-resolution motion boundaries. As shown in this girl's arm and the boundary of birds, our visualization results are much better. Our more results on Center and Kitty can more fully explain our advantages. In addition to these datasets, we also test our model on a real captured dataset, Davis, and our model also obtained better results, especially in the small motion area and high-resolution motion boundaries. For example, the boundary of the vehicle, the fence and the dark, and the people who are playing basketball. However, in large motion areas, in large motion blur areas, our model and raft both have some error estimates. The submission of results was jointly trained for 200,000 iterations. We have tried 400,000 iterations after challenge submission. The results was so much better. It won the first place on Kitty. The metric has been improved by more than 17%, but on other datasets, the results are basically unchanged. We consider that this may because our proportion of Kitty is large, and 200,000 training iteration is not enough for our model. Due to the quarter resolution correlation in our model, the memory consumption is much more than raft. Thus, for high-resolution dataset like Viper, we need first downsample the input image, then upsample the estimated flow and multiplied by 2 as the final estimation. In our opinion, the robustness across datasets, the flow in low texture or smoothness, large illumination change, serious motion blur, and the extreme motion of small object regions are still worth of further study. To conclude, we propose to apply primary structure to raft. After experiment, it can achieve accurate high-resolution optical flow estimation, and we got the second place in this challenge. In the future, we will consider how to reduce the memory consumption and achieve more accurate flow estimation, even at half or full resolution. Thank you for watching.
Okay, thank you. Let's see if we get any questions and answers to that. Please post your questions. Let me kick it off maybe. So I repeat myself, I think, but if you look at all the data sets and that especially leaderboards, what do you think was the most challenging aspect of it to combine those data sets? If you could choose one of those to remove to make your life easier, what would it be and why? Hello? I think you're muted. Okay, I think we lost our presenter. Yeah, looks like, yeah, Daniel?
Well, it doesn't look like he's muted. Are you still there, Zhejiang? I guess you're right.
Yeah, I think we continue, and maybe if we get him back on the line, we can do the Q&A later. We come now to the second place for the depth prediction, monodepth prediction task, RMDP. Are you ready for your presentation? Please start sharing your screen.
Yeah. Okay. So can you see my screen now?
Yes.
Yes, it works. Please continue.
Okay. Hello, everyone. In this talk, I will introduce our submission to the track of depth prediction in this challenge. Our team is from Huazhong University of Science and Technology. In this challenge, our goal is using a single model to estimate depth from any single images. In particular, we hope our model is robust and is able to recover accurate metric depths. Okay, let's begin with some related works about robust model depths. Overall, the key idea of these four methods is learning depth from the ordinal relationship of point pairs. Although these methods are able to estimate the relative depths, the relative ordering may be correct, but the relative distance between the objects may turn out distorted. The previous slide demonstrated the ranking-based methods for model depths. In this slide, I will show four recent works based on pixel-wise scale invariant noise. These methods generate ground truth depth data either from serial matching or structure from motion. However, we have no idea about the scale in this dataset, so they all adopt a scale invariant noise for training. In this challenge, we first explored some recent relative depth models. In particular, we chose the best two methods and our work published in CPR 2020. We test methods and our method on the validation set. Note that the two models did not use any data from this challenge. The quantitative results are shown in these two tables. Since the two methods only output depth up to an unknown scale, and they have no idea about the scale information of the KT dataset and the rapid AI, their performance are not accurate enough when compared to the directionally supervised method on the leaderboard, like the DeepLab and PSD. So in order to recover accurate metric depth, we train models on the official provided data, including the KT, Rapid AI, and Syntel. As usual, we base our model on an encoder-decoder architecture, and we did a lot of experiments on searching a good encoder, decoder, and loss function. Finally, we use the pre-trained ResNex 101 WSL and the BTS as our encoder and decoder, respectively. Besides, we designed a feature embedding module based on two observations. One, context information is important in depth prediction. And two, the resolution of trainable images is 9 square, and the weight of the input images is much larger than the height. So the embedding module uses a height-wise convolution, width-wise convolution, and a channel-wise convolution. The receptive field spread across the whole feature maps by combining convolution in different directions. The black arrows indicate the stride direction of convolution kernel, and the green boxes indicate the receptive field. We choose our trainable data in the left box. We use 3 datasets for training. During training, images are randomly flipped in horizontal direction and half resized and cropped to a fixed size. Note that we set the maximum depth to 100 meters when we use the BTS decoder. I'll show some experimental results. Actually, we first validated the effectiveness of our embedding module in semantic segmentation. The yellow point in the RGB images indicates the selected object. The hot regions mean more affinity to the yellow point. Our module makes interclass features more similar and interclass features more discriminative. Here, our method ranked the first on the Rapid AI benchmark. And we show some plots in terms of some specific metrics. For example, the mid 30. Yeah, the pink line indicates our method. And the fake 30, the mix ST, and the fake ST. Here is the results on the KT benchmark. Our method performs not good on this benchmark. Yeah, here is the results on the Syntel benchmark. And the Vapor benchmark. Note that the Vapor did not provide any training data, so we have no idea about the scale information of the ground truth depth data. As we can see, the directly supervised methods like the BTS, IEF, Pagan, SFM, HR, and our method performs poorly on this benchmark. The robustness of these methods are not good. In this slide, we show some cognitive results. From left to right are RGB images, predictions, and arrow maps. One can find that the method fails to predict accurate metric depth at distant objects. In order to analyze the robustness of models, we add dropout layers to enable our model output uncertainty maps. We can see that the uncertainty maps also explain that the model performs poorly at distant objects. Currently, direct supervision achieves better results in terms of these quantitative metrics. However, their robustness is not good. And I think it's better to add more unseen test data in this challenge to validate the robustness of different models. Yeah. If you are interested in model depth prediction, you can contact us via the email. Thank you.
Thank you, Xin, for your talk. Let's continue with the questions for mono depth. After that, we will try to get our second flow contribution back. So we have the Q&A after that. So for Xin, the first question we have in the channel is, what is the reason for having width-wide convolution and channel-wise convolution in the embedding part of your network?
Wait a moment. Sorry, I can't hear the question clearly.
Yes, I can repeat it.
So could you please repeat your question?
What is the reason for having width-wise convolutions and channel-wise convolution in your embedding part of the network?
Okay. At the beginning, we found the context information important in dense prediction tasks like the semantic segmentation and depth prediction. And the second one is the training data, the training data has the resolution of the training data is non-square, and the width is much larger than the height. So in order to get a global information, we we first use height-wise convolution, and followed by width-wise convolution and channel-wise convolution to enlarge the receptive field. So yeah, and actually we find it is effective in semantic segmentation and the depth prediction. So we just use this module in our submission. Yeah.
Okay, thank you. Do we have other questions? Yes, here's another question. How do you combine the width-wise embedding and the height-wise embedding and the channel-wise embedding?
Actually, we first use the height-wise embedding, and then we use the output of this, the output of the height-wise convolution to the as the input to the width-wise convolution, and then followed by the channel-wise convolution. Yeah, just in this way, the sequential function. Yeah.
Thank you. Okay, so I continue with my go-to question. What did you think was the most challenging aspect from your RVC competition? So which of the data sets or which aspect of the data sets and how they differ made your life harder, or the participating at the competition harder?
Okay, I think the biggest challenge is the different depth range. From the KT, the depth range is from the 0 to 80, and for the Intel data set, the depth range is from 0 to 250, and for the Rapid AI, the maximum depth is 100 meters. So I think the depth range is the big challenge, and actually in this submission we set the maximum depth to 100 meters. So I think this is not a good way to train our models, because we have no idea about the scale information of the WIPO dataset, right? And the maximum depth of the Intel dataset is 250. So our method performs not good on these two datasets. So yeah, the depth range is challenging. So and the second one, I think, as we can see in this slide. Okay, June. Okay, let me see. In this slide, the metas did not use any training data from the official provided data, right? Actually, they perform well on this benchmark. So, and other directly supervised methods like the BTS-IEF, package SFM, HR, and our methods perform poorly on this benchmark. And so I think it's better to add more unseen test data in this challenge to validate the robustness of different models. If the test images are similar or same in our training data, their performance would be great, right? If we test the different models on an image that were unseen during training, their performance decrease or not.
Yes.
So I think yes. So I think it's better to add more unseen test data in this challenge to validate the robustness. Yeah.
Yes, thank you. Okay, we will now try to repeat the Q&A session from before. Thank you, Xin. You can stop sharing.
Okay.
the original presenter drop? I don't see him in the list. Zheng Xiao, are you again in the call?
Yeah, I'm here.
Oh, hi. Okay, so we can continue with the questions. So we already got one question in the chat, I think. Yes, from Jonas. But Jonas, you can go ahead and also voice your question, I think. But
sure.
Yeah, go ahead, please.
Hi. So yeah, I was wondering, you use these two different pyramid levels, and I mean, part of the reason why Raft doesn't need that, right, is that they kind of do the, like, basically compute the full cost volume across all pixels. But now one could think, okay, in your finer resolution, you already have the basically the estimate from the coarse one. So I was just wondering, why not use for your finer pyramid scale a reduced cost volume, like, for example, PwC is doing?
Reuse the cost volume. I don't understand. Yeah, please.
So, okay, so what I'm saying is, if you compute so in this slide, the upper block, right, for the fourth resolution, yes, so you already have a pretty good coarse flow estimate from the other scale, right?
Yes.
Yeah. So then why do you need the full Raft step with which kind of computes the pairs between all pixels? Wouldn't it be enough now to kind of just look within a smaller region for this finer resolution cost volume instead of looking across the full image?
We think the high resolution feature can preserve more image details. So we repeat our updater again on quarter resolution. So this our results only also prove these advantages.
Okay, thank you.
Is there a second question? Please type it in the Q&A. Okay, so given the time, we should continue. Thank you for the Q&A. The next talk is the second place of the object detection challenge. Why is that? Who will present? I think we have two people who were online.
Hi, can you see the slides?
Yes. Hi, Gary.
Okay.
Please start.
Okay. Sorry. Okay. So I'm Fan Jiaqi on behalf of my colleagues Huang Junxing and Yu Xiaochuan. I'm very excited to share our second place solution to the object detection track. So OID, MAD, and COCO each have very different internal properties. For example, OID is the only dataset that has hierarchical label structure. And it also has many label noises. For example, some of those images does not have complete labels. For MAD, its images are mostly collected from smartphones, so some of those could be quite large. And this has a lot to do with the tiny objects. And some of those objects have extreme aspect ratios, for example, the pose and manpose in those pictures. So to deal with those, we chose three powerful backbones, CFNet, Detector RS, and Grid RCN. We also employed tricks like cascade head, deformable convolutions, and IOU balanced sampling. we also trained 3 expert models. So we chose based on the validation performance of those different base models. So we chose classes that have the lowest average precisions, smaller than 0.1, and the average precision between 0.1 to 0.15. We also selected classes that have the smallest average object sizes. So that gives us 3 expert models. And for the data augmentation, we used multi-scale training and random horizontal flips. For our expert model training, we used random crops to the size of 1024 by 1024. And we also use multi-scale testing during inference. So the dataset imbalance issue is huge in this competition. To address those, we use a offline data sampler. Basically, we calibrated the importance of images using an approach that is very similar to TF-IDF. And we performed weighted downsampling to give us subsets of training data. So they are smaller in size and also more balanced. Besides offline data sampling, we also used soft balanced online data sampling. So following the previous work, there are basically 2 approaches, class agnostic sampling and class aware sampling. The class aware sampling will unavoidably train the minority classes over and over again and lead to severe overfitting. But the class agnostic sampling will just let the performance of the minority class suffer. So to strike a balance, we added a lambda parameter to regulate the class-aware sampling probability. But still, we found some of those samples as not being trained during the training. So we followed the previous work and adopted hybrid training schedule. So basically, to train our models with non-balanced sampling first, and then use the soft balanced data sampling. Another trick we used is budget-aware learning array scheduler. So conventional learning array schedulers are basically designed to let it train until convergence, but we are under severe time constraints. Many of the models doesn't even finish like 2 to 3 epochs. So we want to have a learning array schedule that performs optimally given certain time constraints. And the linear budget-aware learning array scheduler is is an efficient way to do that. So it basically just drops the learning array to 0 when training ends in a linear fashion. And this has shown superior performance even comparing with adaptive learning array schedulers. For post-processing, we used 4 different NMS, just naive NMS and soft NMS and adjusted NMS and hierarchical NMS. But we didn't find any significant improvements for the adjusted NMS and hierarchical NMS. So we just adopted soft NMS for all the models. For ensembling the 6 models, we simply join the predictions on the unified label space and form a naive ensemble with equal weights per model. And our benchmark-specific post-processing steps only involves removing predictions that do not belong to the specific benchmark we're submitting to, and remap the unified label space back. So there are many issues we found with training data sets. So for example, MAD has duplicated bounding box IDs, and some of those image dimensions are actually wrong. So the height and weights are actually reversed. There are some out of the image boundary bounding boxes. And we also found two bounding boxes on COCO that have 0 area. So these issues will obviously introduce numeric instability and break our training. Another thing is that in OID, last year's winning solution found that some of those classes some of those leaf classes have label confusion. For example, torch and flashlight. They should have been the same class. But this year, we also found that the label confusion does not happen just on the leaf level, it happens on the parent level as well. So for example, persons and mammals, they're both parent level classes, and they do not share parent-child relationship, but they are labeled interchangeably, for example, in this plot. Another thing is that has a higher impact than label confusion at the parent level is a missing leaf, because OID basically prioritize leaf classes over parent classes. In this example, as the helmet only has two children, bicycle helmet and football helmet, but neither those child classes could represent those helmets in this image. So it just labels with a parent label, with a parent class. So this will cause issue during training. So these are the challenges, but still we were able to achieve such results on the 3 separate benchmarks, and that gave us a second place on the overall leaderboard. So that's it. Thank you, and let me know if you have any questions.
Thanks for your presentation and sticking with the time. Let's start with the questions. I will kick it off by asking about, so this is the first of the presentations where we have a lot of label confusion issues. So how did you manage to basically split or merge labels in label spaces that are disjunct or have some partial overlap?
For example, if we found some classes in COCO that should have been the same class with OID. For example, like maybe if I recall correctly, backpack occurs both in COCO and OID, so we just merge that class. We have one backpack class in the unified label space. And another thing we tried to do is to use a concurrent softmax, which basically tried to calculate the concurrent or co-occurring probability of 2 classes, for in this case, torch and flashlight. So if they occur very frequently in the annotation space, then we adjust their losses accordingly. But we have mixed results with this concurrent softmax, so we did not use it in the final submission.
Okay, and there are labels that in one data set combine labels of another data set. So how do you handle this in the unified label space and then at the submission time?
So you're talking about post-processing, sorry?
For example, but also for the training. I mean, you have to select your unified label space in such a way that you represent the finest detail, or at least that's what I would do. And what do you do if you don't have this information? If you have, as you said, for OID, there are some examples where you don't have the leaf nodes. You can also have data sets where the annotation is not a leaf node of another data set. So your unified label policy might have it as a leaf node, but in that one data set, it is a hierarchical category below it. So how do you split this, or how do you get this ambiguity out of the data?
So I think for this composition, OID is the only one that has a hierarchical label space. So it only happens if the leaf class in OID are missing, but not in the other class, not the other way around, I guess. But so for your questions, we followed.
Gary, excuse me, I'm a colleague with Gary. Let me answer this question. As we know, only OID has parent and child relationship on labels, but some parents labels like person and car, it is parents label on COCO, but but they are just leaves on they are parents on OID, sorry, and but they are just leaves in COCO. So we just regard this such
categories as a leaf class in our unified map, and we only find around 27 parent labels on OID. It is just the second layer, and the other labels are we all regarded as leaf nodes.
Sorry, I didn't get the answer. How do you handle then these non-leaf nodes? How do you solve the label? Do you throw them away, or do you map them to one of the leaf nodes?
Oh, yeah, we just we map the parents. We map the parents nodes also as a category. So finally, we have 530 categories, and there are only 27 categories. It is they are just the parents nodes of OID, but the remaining is just the leaf nodes. We regard it all as leaf nodes. For example, person, class, birth, such categories are parents categories on OID, but we regard it as a leaf.
Okay, I see. Thank you.
I think what my colleague are trying to say is that if we just simply throw parent classes away, for example, in this case, we would lose those helmets bounding boxes. That's there's no way we could recover those. So that's why we chose to keep parent class in our training set.
Yes. I got some questions from the audience. What is the training loss over the unified label space?
It's just It's just a simple cross entropy, as in a single model on a single dataset. We did not change that.
Okay, so this is basically in a pre-processing step. You join the datasets, and then it's one training loss for the whole thing, right?
Yes.
I think this answers the second question, but I'm still gonna ask it. Is this a large softmax cross entropy over all classes? Basically, yes, right?
Yes. So, for example, if we have 500 city classes, so that's each model has each bounding box head has 500 city classes.
Mm. Did you ignore classes outside the source dataset during training? I think this
datasets.
Yeah, I think this refers to if you know that one of the training images comes from a certain data set, do you automatically ignore all labels that are not part of that data set, of that data set? Do you use basically this information as negative labels somewhere?
No, we did not use dataset specific information during training. I think isn't that violation against the rule?
Sorry? I didn't get the last part.
Isn't what you just said a violation against the rule to
not
use
during training time this is allowed, but during prediction time, of course, you should not use the information of the data set, the source of the data set, while supplying it. But generally, we do think that it is a bad choice, of course. But adding the negative labels themselves can, of course, help, because this is basically like you have a unsupervised step with it, basically, that says, okay, I know in this image there will be no elephant, just because the data set itself doesn't have any elephants in it, you know, something of this that is totally fine with the rules. Okay,
yeah, that's a very good point. So basically, we saw solutions that try to alleviate that issue, that conflicting label space issue at the loss level. There's a paper in that sort of modified focal loss to do that, but that will lead to dataset specific losses, you know. So basically, the loss will need to know which dataset the sample is from. So we did not go that direction. Another direction to address that is to use, for example, a model that performs well on a single data set and use that to produce pseudo labels on the other data set. So presumably that could help that situation. So basically trying to pad annotations. I guess that's one of the areas that we want to explore, but we didn't have the time.
So we have another question from Rodrigo. Did you use the negative labels from OID that OID supplies in any of your training steps?
No. Okay. We only use positive labels.
Okay. Okay. So given the time, I would say we have to move on. Thank you. Thank you for the presentation and the interesting Q&A. We continue now to the Panoptic segmentation task, the first place, the winner.
Yeah, sure.
Yes, Rohin, please.
Okay, yeah, I can share. So it's sharing, right?
Yes, now we see it.
Yeah. Hey everyone, I'm Rohit. I'm a master student at University of Freiburg. I work as a research assistant at Robot Learning Lab, and I participated in RVC challenge under the supervision of my professor Avinav Valada. And I'm here to present FPS B1 BS4 RVC, which is essentially a lightweight version of efficient PS, our previous work. So before we start talking about our efficient PS or FPPS, we talk about panoptic segmentation, which is combination of semantic and instance. So in semantic segmentation, we have no reasoning about instances. It's just dense prediction. In instance segmentation, we have no reasoning about amorphous regions. And then finally, we have panoptic segmentation, which combines both of them. And we can see panoptic segmentation as dense class predictions with delineation of object boundaries. We'll briefly go over panoptic segmentation track for RVC 2020. The aim is like encouraging development of robust solution on a variety of data sets. For this, we were supposed to train a single model over a joint data set comprising of 6 different data sets, although Kitty was taken out later, but yeah. And we had to benchmark individually on each benchmark server. So for this, we employ a lightweight version of our efficient PS. We'll talk about it later, which we refer to as FPS B1 BS4 RVC, which achieves a rank 1 in RVC 2020. Before we talk about FPS, we talk about efficient PS. So in overview, we give an input image, the FPS processes it, and we have semantic prediction as an output, then class prediction, bounding box prediction, and mask predictions. And all these 4 outputs are used by Panoptic Fusion module to finally generate the Panoptic prediction. So here we have the efficient PS architecture. It is essentially comprised of an encoder and two-way FPN, which forms the entire backbone, which is the left side of the image. Then we have a semantic segmentation head, and then instance segmentation head, followed by the Panoptic Fusion module to generate the final output. In case of the backbone, first we talk about encoder. The encoder is essentially from the CFNet family, and we use CFNet B5 as our official backbone encoder as part of the network, which was found using NAS and uses compound scaling. We use it because it has rich representational capacity with fewer parameters and flops in comparison to other encoders out there. We modify it minorly by dropping the squeeze and excitation connections and use in-place activated batch norm synchronized version with leaky ReLU in place of the standard batch normalization and ReLU activations. We again propose a two-way FPN, an alternate version for a standard FPN, which allows any bidirectional flow of information. In standard FPN, we have a top-down branch that predominantly propagates semantically high-level features. To this, we add a parallel bottom-up branch, which predominantly, again, propagates low-level features. And then we aggregate features from both branches, which results in a richer multi-scale representation. Then talking about the semantic head, it's also, we propose this in our paper, where we try to operate on different scales differently, where large-scale outputs predominantly contains fine or characteristic features, whereas small scale outputs comprises of features rich in semantic info. So we use scale dependent processing, where we use the dense prediction cells for small scale, and LSFE as proposed in the paper for large scale outputs. These variable scale features are aggregated in bottom up manner, and then we follow it by semantically reinforcing fine features for better object boundary refinement. This concludes the semantic head. And in instance head, it's basically a standard mask RCNN. We just replace the standard convolutions with depth-wise separable convolutions to reduce parameters, and otherwise it essentially remains the same. And then we have the final part, which is the adaptive panoptic fusion. And it focuses on resolving overlapping prediction of semantic and instance head output by selectively attenuating or amplifying the contribution of each head, for which we have mask logits from MLA from instance head, and then mask logits B from semantic head, and then we fuse them according to the given equation. So we briefly walk towards how adaptive panoptic fusion works. So let's say we have 16 instance classes, and we have the output mask logits, bounding box spread, prediction, class prediction, confidence. We apply confidence threshold, reduce instances. So we have now 8. Then we sort it based on confidence, scale it, resize pad to get to the original size of the image, the resolution of instance masks. And finally, we apply overlap threshold to again reduce the number of instances to compute the mask logits A, which could be seen as essentially an NMS. So after MLA, we parallelly compute from semantic logits and the bounding box predictions, as well as the class predictions, a mask logits B for the same instances as computed in mask logits A. And then we use the fusion equation to generate fused logits. Once we have the fused logits, we use the stuff logits from the semantic logit part to concatenate them together to finally compute the intermediate logits. From this, we can apply argmax or softmax to get intermediate prediction. And to finally get the panoptic prediction, we zero out all the stuff prediction in intermediate prediction, and then fill it with the stuff prediction from the semantic branch to get panoptic prediction. And this is in a nutshell how adaptive panoptic fusion works. For FPS B1, BS4 RVC, we essentially replace EfficientNet B5 with B1 and use standard mask RCNN, that is without any depth-wise separable convolution involved. And why we do it, it's because of resource constraints. Now talking about the datasets involved were Microsoft Cocoa, Cityscapes, Mapillary Vista's dataset, and Viper, Wildash, and Kitty for Panoptic Challenge. While combining these different datasets, the problems that can be faced are different annotation schemes. So for example, in Cityscapes, you have pole, which belongs to as stuff class, whereas in MVD, it belongs to thing classes. And similar discrepancies are there throughout the data set. Then we have variation in environments. It can be indoors, outdoors, simulation environment. And the third, we have like imbalance in the number of images available for training. So this can lead to overrepresentation of a data set or underrepresentation of some other data set, which can make the model biased towards some data, a particular data set, or couldn't even detect some other data set. So to tackle them, we mention it as in data augmentation, what we did. So for the discrepancy in the labels, we create a unified label mapping space where each stuff and thing classes are treated uniquely, irrespective of their class being the same throughout different data sets. What it means is like pole in Cityscapes is now, it's a unique class of its own, and pole in Mapillary Vista is a unique class of its own. And thus we have 109 thing classes and 77 stuff classes. Similarly, for moving on to the imbalance thing, we replicate all data sets exclusive of Cocoa 3 times, and then combine it with Cocoa to form our joint data set, or what we call epoch. Additionally, we limit the longest side of Mapillary Vistas to 1920 pixels because of memory limitations. And we also apply random data augmentations, flip and scale. And finally, we have a variable crop sizes. That means whatever the original size of the image, let's say Coco, if it's 640 cross 480, then 640 cross 480 is taken as the crop size. And if it's cityscapes, if it's 2048 cross 1024, then the crop size is taken as 2048 cross 1024. So that's for data augmentation. And for the training protocol, it's the standard one. We use ImageNet pre-trained initialization as well as Xavier. We use SGD with 0.9 momentum along with multi-step learning rate. Although we use just batch size 4 because of the number of GPUs available, each GPU can host only one image. So we use 4 GPUs, so 4 batch size. We train it till total epoch of 10. The important thing is, due to time limitations, we were only able to train the benchmark model on training set exclusive of the validation set. And during testing, we do test time augmentation such as flip and multiscales for Coco and cityscapes, as shown here. We also upsample output to original image size where it's not there. For example, Mapillary Vistas, we get output at 1920 as the longest side. So we have to upsample to 4000, 6000, whatever the resolution is. And then here is the minimum stuff area parameter, which is used in Panoptic Fusion modeling. In the benchmarking, so we achieve rank 1 for Coco and Viper, and rank 2 for Cityscapes and MVD, and jointly rank 1 for Wild Dash. Yeah. So you can here are the evaluation results, qualitative. You can see we have from Coco we have a beach scene. In Cityscapes we have a cluttered urban scene. In Viper there's change in weather conditions where it's rainy, and then we have Wild Dash with clears. So all the data sets have a large variety of scenes throughout, which is challenging due to change in number of instances, a lot of objects, weather conditions, and similarly others. So, oh shit. Oh. What's this? Sorry, yeah. So to conclude, FPS B1 BS4 RVC achieves rank 1 in Panoptic Segmentation Challenge, RVC 2020, which essentially exhibits the robustness of our method efficient PS, as it's just a light version of it. But we can always achieve more performance if we train for more epochs, train with a higher batch size, and inclusion of validation set in the training set, or we do everything together. So finally, thank you for your attention, and we will release the code at rl.uni-freiburg.de once our paper is accepted. Yeah, and that's it. Thanks.
Okay, thanks. We already have one question, I see. Yes, this was something I was also wondering after hearing your presentation. If you're basically multiplying the label space and you keep the labels of each data set separate, right? So there is a duplicate label, although it is semantically the same. Is that something we understood correctly?
It was a simple, logical approach to just make it different. So it's not a very, would you say, efficient way to do it. It was just a small logically, so that the network doesn't confuse between stuff and things. That was our priority. And so, yeah.
And so all the stuff, did you do some merging of labels in the stuff category, or did you also duplicate stuff labels?
It's always duplication. For each data set, everything is kept separate. If let's say if it's thing in other data set, then a thing class is created for that. So for example, pole thing is from maybe Mapillary Vistas, maybe Wild Dash. And if it's Cityscapes, thing stuff is created for Cityscapes, and then your, let's say, Viper. So it's something like that.
Okay, I have to ask you to do an offline session with me, so we get to the point of it. Because if you really duplicated all the labels and you have basically separate detectors and classifiers in there, then this is against the rules. So the rules.
No, there's no separate. It's like I think I sent you the Panoptic label space. So it's just from mapping where you have just yeah, it's just simple mapping thing.
Okay, we'll handle this offline. Let's continue with other questions, please. Is there anything in the Q&A?
I guess this may be a related question. So if I look at the Cityscapes ranking, I see that the FFPS RVC submission is quite a bit lower in quality to the efficient PS itself. So I guess part of it is because you simplify the architecture due to the memory needs. But I'm curious, I guess if you observe some of the benefits of training with the extra data compared to baseline that only train on Cityscapes, for instance.
Yeah, it's because of the memory requirements and like time constraint. We didn't. It's the model that we submitted is not the optimal version of efficient PS. It's just a very light, very unoptimal version. So yeah, that's why the performance difference is there.
And the second part, did you see a benefit from training with additional extra data from the other data sets?
Well, from the results, I wouldn't say that I saw anything, because for Cityscapes, we got just 48, whereas without even just training Cityscapes, we can manage to 63. But it's because of the confusion between a lot of classes that needs to be predicted at the same time. So that
just to drop in one comment, by combining multiple leaderboards in all the tasks we have labels, of course you have a much harder challenge to solve. In the case of optical flow and stereo, you basically solve the same task, and if you add more data, at least ideally you would increase your robustness, because the challenge and then the difficulty stays about the same. Of course, you have different dimensions, different disparity ranges, but apart from that, it's basically the same task. But in label, so all the tasks with label spaces like object detection, all the segmentation tasks, you actually increase the difficulty. And so maybe my question to you, or as a follow-up to Rodrigo, would be, there are data sets that share a lot of same labels. So do you think leaving out some of the data sets would have worked and would actually improve the overall RVC submission? Not all of them, but...
Yeah, if it was the case where it's the same labels throughout, if we would have leave out some data set, it would perform better on the other data set. That would be the case. But here we were like going for everything, so it's like in some we got a better performance, but we suffered in the urban scene, like for for MVD and Cityscapes. Maybe again it can be rectified if we had a much more representation, maybe more if the training during the training, if it saw more of Mapillary or Cityscapes as we did, it might have improved the performance more.
I see. Okay, given the time, I'd say we close up this Q&A. Thank you, Rohit.
Yeah. I can stop for share. Oh, it stopped, right? Yeah. Okay.
Yes, I will now share again my screen. Let's see. Can you see the screen? Okay. Yes. Okay. So those were the presentation by the challenge winners. Thank you again for taking the time and doing these great presentations and also answering the questions. We will have a second session. This will be in 8 hours. This is for the remaining winners. And with a bit of luck, we will also have some of our keynote speakers with us so we can discuss the topics in the keynotes. Maybe as a last topics to close up this session, one thing that resonates with me, or that is a very strong point in all of this, is if we add more data, if we add more test data, if we have more data points, do we get a better evaluation just because we have more data points, or do we get a more robust evaluation because we choose those data points strategically to be different than the existing data sets? So what I'm saying is, if one is to create a new data set, what is the most important part of it? Is it just quantity, or is it quality? How do the two things correlate? This is a question for the organizers. So maybe Daniel, you have a lot of things going on.
Well, I'm happy to. I already mentioned my opinion on this earlier, and of course very biased towards pixel labeling things like stereo and flow. In my mind, quality is much more important than quantity. I mean, in some sense, the deep learning revolution has made it about quantity, at least as far as training data is concerned. But I think it's, as far as test and validation data goes, it's actually a good idea to have a very small but very diverse validation set, and to not just look at numbers. The problem with deep learning is you always need to have a single number that's your loss, and it's very hard to define a loss that really captures all the things that you care about in real life. So as you know, on leaderboards, you often have a lot of metrics, and you're encouraged to look at a lot of metrics. But I also find visualizations incredibly important, and
I agree.
So,
yes.
Yeah. Anyway, that would be my take.
Maybe as a different point, Rodrigo, how's your view on that? I mean, OID has a lot of content.
Well, I mean, yeah, I think it was also just mentioned before. I think the diversity. I mean, in the optic of robustness, right? Usually, robustness is in the context of robustness in the real world, which then
yes.
you want to cover as much as possible of the real world. So I will say the smallest quantity that has enough diversity at the quality that we can afford. That's
a bit of cheating. I mean, sure, but how do we achieve that?
Well, I mean, okay, so concretely, for instance, OpenImage is heavily imbalanced. And I think for evaluation, it doesn't make sense to evaluate over very imbalanced categories if we want to be application agnostic, right? If you know your application is, I don't know, to recognize the most common object in the world, then sure, you want to represent the natural distribution. But if you want to be somewhat application agnostic, then every single class we know of is equally important, right? Like Sprinkle cans is just as important as golf balls. Then you want to have whatever, like 10 examples per class, but I have a lot of classes. And then, depending on how many classes you do, then there will be that will make a lower bound of how many instances you want to annotate. And then how good is the quality of the annotation will depend to some extent to the budget you have. It needs to be good enough that you feel that you're measuring something sensible, but not the last 20% of quality costs most of the money, right? So usually there's a trade-off to be made there.
I want to take the opportunity to give a plug for Ross Gershik's invited keynote for that relates very much to this question, and the idea that if you do something like segmentation or recognition, and you just have a well-defined class of objects, that's a very kind of unnatural problem, and the real difficulty lies into dealing with what he calls the abundance of the range of abundance, so that you have some examples where you have thousands of instances and others where you only have one or two, and to be able to deal with that. So if you haven't done it yet, watch all the keynotes, and in particular Ross's keynote speaks to this.
Yes, I was just about to comment as well. So as you might surely know, in the Elvis data set, they use this approach to basically attack this long tail distribution of occurrence of objects, and few shot learning is of course a big topic currently. But Rodrigo, if I got you correctly, you said that the best or the ideal solution, if we have the money for it, is to actually don't tackle it as a few-shot learning problem, but to really try to hit it with a lot of data, to really have, even for this long tail, to have enough examples, to have a lot of diverse examples, right?
The few-shot is about the training. The question was about the evaluation. So for evaluation, there's no replacement having at least some instances annotated, right? And then the question is how many is enough? It's actually class dependent, but no, I was mentioning 10, right? Like when you start covering many classes, then you cannot afford to have 1,000 instances per class. And also some classes are actually hard to find that many instances in practice. So yeah, it will be much fewer instances that we're used to now, but over much more classes. And again, for evaluation, there's not much you can do. We have some ideas of stuff you can do there, but no, probably next CVPR, we'll talk more about that.
Okay, interesting. Yeah, with that cliffhanger, I think we close the first session. Thank you all for joining. Please take your time if you are still awake or again awake in that time zone. In 8 hours, we'll have our second session with a lot of additional good winner talks, and I'm very much looking forward to it. So thanks again, and yeah, see you in 8 hours.
Yeah, thank you. Bye-bye.
Bye.
Thanks to all the presenters. Bye.
Thank you.